Welcome to class, students. We will be beginning Chapter 9 today, and Chapter 9 is all about functions. So we've studied lots of different families of functions in this course so far, and so we're going to be looking at some other details about functions in this chapter. And we're going to start off in this lesson with looking at multiple representations of functions. We've seen functions represented by equations. We've seen functions represented in real life problems in words, or your favorite story problems. We've seen functions represented in graph form. And so we're going to be looking in this lesson at multiple ways to represent functions. And we'll also be looking at how we might read graphic representations of functions and gather information from them. So our learning goals are to translate between the various representations of functions. So we'll translate between the different representations and then solve problems by using the various representations of the functions. So we'll also solve problems. Now I mentioned all the different ways, many different ways that you could represent functions. Here's an example of one scenario and represented in many different ways, 4 different ways to be exact. The first way is in words. An amusement park manager estimates daily profits by multiplying the number of tickets sold by 20. Then that would be in the word format. In an equation, we could say P, meaning the profits, is equal to 20 times n, or if we wrote it in function notation, we could say P of n is equal to 20n. We could represent that in a table by giving some specific instances, like if we sold 50 tickets, we would make 50 times 20, which is $1,000 in profit. 100 tickets sold would make $2,000 in profit, and so on. So you have table format. And finally, in graphic format, we could take this function or even just the points that are listed in the table and plot them. We would see that they actually form a linear function, and that graph could be used to answer questions, make predictions, and just represents all of the possibilities, where the table might just have some specific selected points. The graph with the arrow showing it goes on forever represents all the possibilities. So in our first example, we're going to do a graph to verbal description. So we're going to take something that's a graph and we're going to convert it, translate it. In other words, that was our first learning goal. Translate it to a verbal description. So basically, we're going to take a look at this graph and see if we can describe what's going on in this situation based on what the graph depicts. So here's the scenario. The graph shows the number of cars in a high school parking lot on Saturday beginning at 10 a.m. and ending at 8 p.m. Give a possible interpretation or verbal description for this graph. So we see that there's parts of the graph that are increasing, parts of the graph that are staying steady, parts of the graph that are decreasing. So what might cause the behavior of the graph in these instances? So why don't you take an opportunity, pause the video now, and see if you can describe what you think is going on here in the graph. So go ahead and pause the video now and give a verbal description of what's going on in terms of the cars in the parking lot on this Saturday morning. Okay, so here's what I came up with. This was my interpretation. I thought that this was the parking lot of GLHS. So I said the parking lot of GLHS was empty at about 10 a.m. So we can tell that's where the graph begins, right here at about 10 a.m. because it looks like they're going by 1 hour increments. So that's 10 a.m. And then the cars began to arrive. So along this stretch here, you can see that the number of cars in the lot is increasing. And then at this next point, the graph flattens out. And what's happening here is no cars are coming in, no cars are leaving the lot because the cars began to arrive due to basketball practice that's being held from 11 a.m. to 1 p.m. So that's why all those cars are steady. There's no change because the people are there at practice, they're staying, no one's leaving, no one's coming. Now after practice, most of the cars left the lot, but a few remained. So that was what's going on here. It didn't get all the way down to the bottom, but most of the cars left and a few people remained. And then some left a little later, and so you kind of see that going down a little bit more. And then something happened here, and it was right around 4 o'clock. And right around 4 o'clock, now the number of cars began to increase. So what was happening here is the cars began to arrive between 4 and 5 p.m. for the choir concert that was going on in the auditorium from 5 to 7. So, of course, once they got there, they wanted to stay for the band concert from 5 to 7. So that's what's going on here. You see this steady amount of cars in the parking lot. No one's coming, no one's leaving. And then after the concert, of course, they are going to head home. And so that's what we see going on here in this last little section is we see the cars leaving. And not everybody was gone from the lot by 8 p.m., but hopefully not too long after that. They would leave the school for the night. So that's an example of a verbal description of a graph. And, basically looking at like the increases in the graph, the flat spots. I mean, what those mean is that we've got no change going on, the decreases in the graphs. And then, paying close attention to the axes, the scaling, what time of day it was, would be really helpful if we had known what the vertical axis, how it was scaled, because we could have been more exact about how many cars were actually in the lot. Well, in our next example, we have some graphic representations, and we're going to see if we can match up each of these graphs with the description of what's going on here. So it says a manager at an amusement park monitors the ticket sales at the park over a 4-day weekend. Match each situation to one of the following graphs. So what I'd like to have you do is pause the video and see if you can figure out which graph goes with A, which graph goes with B, and which graph goes with C. So please pause the video now and complete the matching of the graphs with the descriptions in A, B, and C. Pause the video now. Okay, so the first description was the park was closed on Friday for repairs. Well, clearly that must be associated with graph 2. So graph 2 is A, or you could say graph 2 over here. And the reason why I know that for a fact is if you notice this point right here on the graph on Friday is at 0. So the park was closed. There were no ticket sales at all on Friday. So that was a big clue there that had to go with graph 2. The park hosted a big concert on Saturday and a parade on Monday. So if you had a concert or a parade, you'd expect to see spikes in the graph on those days. And here in graph 3, you see a spike there on Saturday night for the concert that was Saturday night, and then the spike on Monday for the parade. And so clearly this is graph 3, and that means this is associated with B there. And then finally, the park was very busy during the holiday weekend. So basically steady, busy all weekend. And that goes here with graph 1. In graph 1, you can see that the graph is staying pretty steady there all along the whole weekend. The sales were very high. Now, that skill is really something that I think is one of the most difficult things that we do, and I think that is, getting more exposure to that, getting more practice with that. I think we all benefit. We see graphs and tables and charts and everything, everywhere, whether it be in, the newspaper, in the periodicals that we're reading, or maybe on standardized tests that are so important. And the more practice we get at reading graphs, the better we'll get at it. So let's go ahead and turn the page. So the title of this lesson was Multiple Representations of Functions. So in example 2, we're going to look at a verbal description, a table, an equation, and a graph. So here's the verbal description. Janet is rowing across an 80-meter wide river at a rate of 3 meters per second. Create number 1, a table, 2, an equation, 3, a graph of the distance that Janet has remaining. So we want the graph to show the distance remaining before she reaches the other side, and then answer the question, when will Janet reach the shore? Well, first of all, when we create a table, which is our first representation, we have to think about what values for t make sense. So for time. So when we think about time, we can't have negative numbers. So we want the values to be greater than or equal to 0. So we'd want t to be greater than or equal to 0. Now, what values of distance make sense? Well, when you think about our distance here, the distance that we have to go, the highest value that we would have to go is 80 meters. So we're talking about distances between 0 and 80. So we'd have to have it be less than or equal to 80 meters because then we'd actually be to the other side, but greater than or equal to 0 meters because obviously, negative meters to go doesn't make sense. So we could start off with, at time 0, and we could, think about so at time 0, she hasn't started actually rowing, and so we know she's 80 meters away from the other side, so the distance to go left is 80 meters. Well, let's see, after 10 seconds, and she goes 3 meters per second, so she would have gone 30 meters by that time, so there'd be 50 meters to go. After 20 meters, she would have gone 60 meters, so that means there's 20 meters to go. After 25, maybe went to 25 meters, 25 times 3 is 75, that means there's 5 meters left to go. And then what about 30? Well, if I put 30 in, well, 30 times 3 is 90, so that would actually be negative 10. So that one doesn't really make sense for our situation because she would already be to the other side. Now, what about an equation? Well, if we wanted to write this in function notation, we'd be writing the distance as a function of time. And we could say that she had 80 miles to go at the time, and that distance was going down by 3 meters every t seconds, or we could say negative 3t plus 80. Then that would be in slope-intercept form. So what if we wanted to make a graphic representation? Well, there's different ways that we could graph it. One way we could graph this is to plot the points from our table. So we could go out here and plot the ones we had 0 and 80. That's a point. 10, which looks like somewhere in between, since these are scaled by 3s, it's just past 9 here, so it'd be 10 and 50, so that's right there. And then we could plot the 20 and 20, so there's 21, so just shy of that, and up to 20, maybe right there. And then we have our 25 and 5, so there's 25, and about 5 would be about right here. And then the 30 and negative 10 would actually be off the graph down here. And then of course we could just connect them and we have our line. So another way that we could have graphed this is we could have used slope-intercept form. In our equation that we wrote, we had a y-intercept, which was 80, and clearly that was right here on the graph. And then we had a negative 3 because the distance away was going down by 3 every second. And a final way we could graph would be to plot the x and y intercepts. And to do that, we could just simply alternate in zeros for x, or in this case, I guess it would actually be t. And instead of being y, it's actually distance. So we could plot the t and d intercepts. The time intercept, in other words, at 0 seconds, we could put in 0 for t, and we would have gotten 80, and that's this point on the y-axis right there. And then if we put in a 0 for distance, if we want the distance away to be, we could have put the 0 in for that, and we could have solved to find out what the time would be, the intercepts. So our final thing was to answer the question, when will Janet reach the shore? Well, on the graph, what it looks like is that point right there where it hits the x-axis, or the x-intercept. So that's down here. It would be the x-intercept. That's what it would look like on the graph. What would it look like in the table? Well, it would have looked like in the table when the distance equaled 0. In other words, when the output was 0. And how could you use the equation to get the answer? Well, you could set d of t equal to 0. In other words, put 0 in for d of t and then solve for t. And we could have found out exactly at what time Janet would have reached the other side. So if we actually did that and we plugged 0 into the function, which was 80 minus 3t, then we would have subtracted 80 and then divided by -3, and that would give us our answer. And it turns out to be about 26.6 repeating, or about 26.7 seconds approximately. So that actually represents that point on the graph right there. Okay, it's time to turn the page. Let's look at another example. The table shows the height in feet of an arrow in relation to its horizontal distance from the archer. So it's an arrow and it shows its horizontal distance away from an archer. It says create a graph and an equation and a verbal description to represent the height of the arrow with relation to its horizontal distance from the archer. So in other words, the further it gets away from the archer, what's the relationship between that and how high the arrow is in the air? Well, clearly the example about Janet was a linear function. She was traveling at a constant rate. That indicates linear. But if we're given data like this in a table and we don't know what kind of relationship, what kind of function is best to represent it, then one way we could find out is we could graph the points and we could actually see what kind of function this resembles. Another thing we could do is actually analyze the data in the table. So what we're going to do is check the constant differences to see if we can tell if this is linear. Remember, if the first differences are the same, it's linear. If the second difference is quadratic, things like that. So we're going to analyze the data. So I went ahead and looked at the, and I saw that first of all, that the x's were evenly spaced. So we were all safe there. They were all scaled by 75. Each of the observations was 75 feet apart. So that part's set. And so we can look at the differences. So I subtracted the first pair and I got 53.25. The second ones I got 30.75. Obviously not looking good for linear function because the first differences aren't the same, but let's continue to look at them. The difference was 8.25. The next was negative 14.3. And then finally, I got a difference of negative 37. So I know this means this is not a linear function. The graph's not going to be a line. So then I went ahead and looked at the second differences. So now I'm looking at the difference between the differences and seeing how those change. So I subtracted the first two observations and I got negative 22.5. And then the next two I got negative 22.5. And then I subtracted the next two and I got negative 22.55. Well, that's really close. And then the final I got negative 22.7. So they weren't perfect, but they were very close. So we're going to say this is quadratic data because, or it's almost quadratic. It's very, very close. And so we would guess that a quadratic model would be very reliable. Remember back how we used our calculator to help us write quadratic equations. We can enter all this data in our list. So we would enter the distance from the archer as our list 1, our height as list 2, and then we could go to calculate. So here's our directions here. We go to stat, then calculate, and then quadratic regression, and then hit enter twice. And what will come up on our screen is all of this information, which tells us our quadratic function that best represents this data. So here's how I could write my equation. I could take that data and I could use, maybe I'll round it, say, to 3 decimal places. So it'd be negative 0.002 x squared plus 0.861 x plus 6.523. And that's a very reliable equation because it's 0.99999 for r squared. And by the way, if that doesn't show up, you need to go to diagnostics and turn them on under the catalog. And so that's a very reliable function. In fact, I showed here how I plotted the points and actually then put in that function into the y equals, and you can see that the dots, which are right here, they're sitting right on that graph. So this is very, very closely related to a quadratic function. So our third thing was we were supposed to, well, we had the graph. So here's the graph in the calculator. We could, if we wanted to, and we had a coordinate plane here, we could just plot out those points that we had above, and when we connect them, it would look something like this. And our third step was to interpret the graph into a verbal description. So I got you started. Well, let's see if we can fill in the blanks. Our interpretation would be this, maybe. The arrow was shot from an initial height of, well, let's see, what was initial height? Well, our initial height, if we look up here in the table, was when the distance away was 0. So that height was already at 6.5 feet, so, or 6.55, I guess it was. Now, if instead I had actually gotten it from the calculator's table at 0, it would be about 6.523. But I saw it right in the table. It was already there for the input of 0, so I used that one. The arrow traveled a total horizontal distance of, and here's the process I used to actually find that x-intercept, because we're looking for the x-intercept. And to do that, I can follow these steps. We need to go to second and trace, choose 2, which is 0, press enter and scroll to the left of the x-intercept. So you have to be able to see that in the table, which means you're going to have to change the x maximum to past where that parabola is going to come down. So past where around 450 maybe would be a good place to set that, or 500, and then you can actually have the calculator calculate the x-intercept for you, and it's at about 437.95. Now, other than using the table and that trace function, your best bet is to use the quadratic formula. So that's what you'd have to use, is the quadratic formula on your equation. And anyway, it reached a maximum height of about 99.19. Well, remember, we also talked about how to do max and mins. So how to do a max and a min on, well, in this case we want the maximum because it's a parabola that opens down. We go to trace and we choose max or min, and so in this case we know it's a maximum. And we scroll the left of the maximum and we press enter to choose the lower bound, and then we scroll over the top and to establish the right-hand bound, and then press enter twice, and it will tell us it's about 99.19 feet. And that happened after traveling about, well, so now we're looking for the x coordinate that's associated with that 99.19, and that should also be on your screen, and that's at 215.25. So utilizing the functions on our graphing calculator, we can get a pretty exact interpretation of the situation here with this arrow and its path that it's traveling on. Let's go ahead and turn the page. Now, because some of these interpretations that we're doing are really dependent on getting some exact values, and that we're kind of dependent on our graphing calculator to do that, what I'd like to do is save these last two examples for in-class you tries. Well, actually, it will be we tries. Because that'll give us an opportunity to, as we work some of these together, to explore in more detail some of these functions of the calculator and how we can use this to help us do these other multiple representations, like coming up with our functions rule or equation, taking a look and seeing what the graphs look like, and then also doing a verbal interpretation by coming up with things like the x-intercepts and the maximum and minimum values in some cases, or certain values at different times throughout the graph. So we're going to leave these for in class, and we'll pick up where we left off here when I see you in class. See you then.